Okay, so we want to know, do these data differ significantly from what the biologists have predicted? Okay, so the biologists have predicted this part here. My computer's freaking out. Okay, so this is their prediction, and the prediction is coming from the Punnett square here. So you've got parent 1 with these genes and parent 2 with these genes, and so the values that are here are the offspring. Okay, these are the offspring possibilities. And so then we have, in the null hypothesis, we could write it
of having green, green. So that means having their color be green. Well, there's 4 different possible ways that the genes can interact with each other. And one out of those 4 is big G, big G. So we could say 0.25. We have yellow, green, which I guess I should write big G, little g. Like this, big G, little g, which is yellow, green. So there are 2 of them, so 2 out of 4, which is 50%, and then little g, which is albino, which is 1 out of 4, or 0.25. And so then in the alternative, we say at least 2 of these proportions of color distribution are incorrect. Okay, now as I mentioned, you could write the null and the alternative hypotheses a little bit differently if you want. We could say that the color distribution of offspring of tobacco plants having genetic makeup big G, little g are the same as the hypothesized values from the Punnett square, and the alternative would be that they are not the same distribution. So I'm just going to leave it like this for now. And then I'm going to say where P little g, P big G, little g, and P big G are the proportions, because I want to make sure to define my parameters, proportions of offspring color when to yellow, green. I know this part is annoying, but this is my communication because I'm using parameters here and I want to make sure to define them. So 2 yellow, green tobacco plants are crossed. And get albino, yellow, green, and green, respectively. I'm sure we probably could have written that a little bit more elegantly, where P of little g is the proportion of offspring that are albino, big G, little g are the proportion of offspring that are yellow-green, and GG are the proportion of offspring that are green. Okay, if the conditions are met, we're going to perform a chi squared goodness of fit test at an alpha value equal to 0.05. We were told that here at the top. Okay, so we want to check our conditions. The first one is random. Okay, so we are told that we have 84 randomly selected pairs of yellow-green parent plants. Now we're trying to study the distribution of colors for the offspring, and so even though I have randomly selected pairs of parent plants, wouldn't presumably, if I have randomly selected pairs of parent plants, that they would result in a random selection of offspring as well? So I'm going to write that. So parent plants were randomly selected. Okay, so the thing is, what I'm trying to say here is, I don't want to just say random check, because like you're not communicating well if you're just saying random check. We have parent plants that were randomly selected, and thus presumably the offspring plants would also be considered a random selection. Right, we're trying to see the gene distributions. So I think we're sampling without replacement, so we're going to need to check the 10% condition. So we have 84 pairs, so 840. Does it seem reasonable that there are at least 840 parent tobacco plants in a large population? So I would say it seems, oops, not it seems reasonable that there are at least 840 parent plants in the population of all yellow-green tobacco plants. Okay, large counts. All right, so this means the expected counts have to all be greater than or equal to 5. Okay, so what does that mean, the expected counts? Well, let's see what's going on. Let's go up to this table. Now, you don't have to make a table. You can use lists in your calculator, but I just want to show you kind of normally how you can organize a chi-squared distribution problem. Okay, so the observed values, this is your data. This is from your sample. Okay, so we had 84 total pairs, and it says of the 84 offspring, 23 plants were green, 50 were yellow-green, and 11 were albino. Okay, so here is the idea behind the expected counts. So this is based on the hypothesized distribution and the sample size. So we take, do you remember expected value was n times p? So n was 84, and the expected proportion, let's see, the proportion of green is 0.25. So 84 times 0.25 is 21. Out of 84 possible plants, if the predicted value is to be 50%, then I would expect 42 plants. If I have a sample size of 84, I would expect half of them to be yellow-green, and that would be 42 plants. And so then albino, so if I have a sample size of 84 and the proportion of albino is 0.25, then I would expect there to be 21. And so then the total expected counts should also add to 84. Okay, so you can do your expected counts in a chart like this, or you can show the expected counts. I'm going to say expected counts all greater than or equal to 5 as shown in the table above, because I'm nicely labeled, excuse me, nicely labeled. And so this condition is met. Okay, so my test statistic, I'm just going to borrow from the top of my page here. So chi-squared is the summation of observed minus expected squared over the expected. Let me fix that a little bit. There we go. Okay, so in order to show your work, you should show the first couple of values. Now we only really have 3 values here. So, but if you have a larger distribution, then you really should just show a couple of values, just so you tell the reader that you know what you're doing. Okay, so for the first piece, my expected count is 23. Excuse me, my observed count is 23 minus the expected count, which is 21. We're going to square that and then divide by the expected value. Then we're going to have observed minus expected divided by expected, and then observed minus expected over expected. All right, so you can do a couple of things. You could just calculate this by hand. It's not that hard. Or you could enter some data into a list. Now my lists are kind of a mess here. Let me clean up my list. I'll clean up all my lists. Okay, so stat edits. I've got 23, 50, and 11 as my 3 observed counts. 21, 42, and 21 are my expected counts. So I could go over here to L3 and take, so if I have the header highlighted, then I can go down here and it'll type what I'm doing here. So my observed counts are in L1 minus my expected counts, which are in L2, quantity squared, divided by my expected counts, which are in L2. And so this is going to calculate this O minus E squared over E for each value, 0.19048, 1.5238, 4.7619. Okay, chi squared is the sum of all of those values. And so then I could go out and I could say second list. I can go to my ops and math rather, and I can go to number 5, sum, and I want to sum L3. This is my chi-squared value. Okay, so this is my 0.19 plus 1.5 plus 4.7, so 6.476. This is my chi-squared value right here. So if I want to then find what is the p-value that corresponds, then I need to look at the degrees of freedom. So degrees of freedom here is n minus 1. Now be careful here because this n means the number of categories. So we are talking about color, and we had 3 categories: green, yellow, green, and albino. So this is going to be 3 minus 1 or 2. So if I go to the degrees of freedom 2 and I look for a chi-squared value of 6.4 whatever, I'm somewhere between here. That means my p-value lives between 0.25 and 0.05. Okay, so I ran out of space here. I'm gonna go on to my next page. All right, so here's what's happening. I have this distribution, whoopsie, sorry. And I have a chi-squared value, 6.476. I've got 2 degrees of freedom, and this is the upper tail probability that I'm looking for. In the table, my p-value is between 0.05 and 0.25, whoops, 0.025. Right, so 2 degrees of freedom, 6 point whatever, between 0.025, 0.05. Now I know that you probably are not satisfied with that. You can find the p-value on your calculator. So on your calculator, you can do it in a couple of different ways. I'll show you the ways that you can do it without using the goodness of fit test, just in case you don't have it. So this is a distribution. So I'm going to go to second vars. And notice down here, we've got the chi-squared distribution. So I want to select the chi-squared distribution CDF, cumulative distribution function, because I'm talking about area under the curve. So I want my lower value, 6.476. I pick some upper value that's large, and I have my degrees of freedom. And then I can find the p-value, the actual p-value. Okay, so you can use the chi-squared CDF. You just have to remember that if you're going to use this, you have to identify all the parts. So I'm just copying all this down. Okay, so this is my chi-squared value. This is my lower bound. This is my upper bound. And then this is my degrees of freedom. Here is my p-value. Okay, so if you don't like to give the range of values or the interval of values, then you can use your calculator to do this. And so then you would just describe or make your conclusion like we normally did. So we start off, since my p-value of 0.039 is less than an alpha of 0.05, that means we reject the null hypothesis. This means that we have convincing evidence that the color distribution of yellow-green tobacco plants is different from the biologist's claim. Or what they predict, I guess you could say claim, or since it said that they predicted it. Okay, I do want to show you, you could do this as a test. So back up here, where's my paper? Here it is. So you still have to show your work, right? So you still have to show numbers plugged into the formula. You don't have to show all of this individual work, but you have to show the chi-squared value, and you have to show your degrees of freedom. Now you don't have to show the n-1 business. So if we go to stat test, we go down to the goodness of fit test. So notice that you have to already have your data in your list, which we do. We have our L1 list is our observed counts, and L2 are my expected counts. We have to change the degrees of freedom to 2, and then I calculate. And so it tells me everything I need. Okay, now here's the thing. If I use this calculator step, if I go to stat test and I do this, don't write anything down calculator-wise. Only if you are using the CDF functionality do you write down this business and label them. Okay, so it says which component in context from example number 1 contributes the most to the chi-squared test statistic. So I want to notice that you can see this in a couple of different ways. One is here at the very bottom, it says CNTRB. This means contribution. So this is telling me each of the values for each of the colors. And we already calculated this by hand, by the way. When you do O minus E squared divided by E, you're actually calculating each individual cell's component or contribution to the chi-squared distribution. So we've got 0.19, and if I use my right arrow here, I can scroll to the right. I've got 1.523 and then 4.769. Okay, so which component contributes the most? Well, the albino. So this is what this is saying is looking at how far away, observed versus expected, this difference is a small difference. This could just be because of sampling variability. Here I've got a slightly larger difference from 50 to 42, and here's how much that cell contributes to the sum of the chi-squared test statistic. But this one here, my observed value was 11. If my sample size was 84, we expected there to be 21 albino plants. And so this one is the highest contributor to the chi-squared value. Okay, so how would I say that then? I would say the color, albino, maybe words are hard here. The color group that contributes most to the chi-squared test statistic is the albino. What was happening here? We had 10 fewer than expected, right? So there were 10 fewer albino plants than expected. So when you talk about which cell contributes the most, it says don't focus only on the size of the component, but also the direction of the difference. So there were fewer than expected. You could say there were 10 more expected than what was observed. It doesn't necessarily have to be in a particular order, but you should discuss the difference there. Which way did it go? Okay, so that is it for our goodness of fit test. Next time we're together, we'll talk about the other two types of chi squared. And so sorry about all the videos today. I hope you have a good rest of your day, and I'll talk to you soon. Okay, bye.